Hello my friends, this is lecture 15 on magnetism and magnetic field. In this lecture we will mainly look on the magnetic field as a vector and understand it. Mainly we will focus on permanent magnets. We have small experiments we can easily perform. If we have a magnet and put it inside a bowl of water with a cork where it can freely rotate, it will rotate and align itself along the magnetic field of the Earth. And this is actually how, I'm going to call this P Earth. This is how compass needle works. It's actually a small magnet. It aligns itself along the magnetic field of the Earth. Of course, align itself along this parallel component. And anytime we have a magnet, it will have a north pole and south pole. And north pole and south pole looks like plus and minus charges in electricity. And if we try to put two north poles together, they will repel, or two south poles alike. And if we put a north and south pole together, they will attract. So like poles repel, unlike poles attract, very similar to like charges repel, unlike charges attract. If we perform another experiment by cutting a magnet in the middle, so the magnet has north and south poles, we cut it, we will see that it will again have north and south pole. We will never be able to make a magnet that has only north pole or only south pole. This is experimentally known. We don't know why, but we can never have a fully north or fully south pole a magnet. Magnets can pick up objects, as we all know, and an object can be magnetized by a magnet, and it itself can pick up an object. That's another small experiment we can easily do. So this is a summary of what the magnets are, what their properties are. If we put a magnet close to an electroscope, if you folks remember, electroscopes leaves opens and so on if we have charges. But if we put a magnet, nothing will happen to the electroscope's leaves. They will not open. So magnetic field doesn't show the same effect as the electric field, but it has similarities. We can use a compass to define which side is a north pole, which side is south pole for a magnet by aligning a compass beside it, and the red side of compass will always show the north pole of a magnet. And doing that, we can identify the north and south pole. That's general properties. Magnets has magnetic field, and magnetic field is a vector. It's a very similar property to electric field, as we recall from electric field. If we have an electric field in an area, we put an electric dipole. This is an electric dipole. It will rotate itself along electric field. And we discussed why that happens, right? Electric field will be pushing on negative and positive charges in opposite direction, and it will rotate it because of those forces. So similar things happen when we put a compass in a magnetic field. Here we have a compass. Magnetic field is upward, the background magnetic field. When we put it in there, it will align itself along that background magnetic field. And that's the same happens for a magnet as well. If we put around a magnet compasses, they will always direct along the magnetic field. We can map the magnetic field lines and magnetic field vectors using that. Or we can put iron fillings around a magnet. Iron is strongly affected by a magnetic field, and they will align themselves along the magnetic field lines, as we can see in this picture here. So we can clearly see, here are my magnetic field lines and how they align. And I can use a compass to find the direction of magnetic field at certain points. And I can map my magnetic field line. Here is my magnetic field. Here is my magnetic field at this point, and so on. And that can give me an idea of how the magnetic field line of this guy changes. If I draw these lines, they will be going away from north and towards south everywhere around my magnet. And that's how magnetic field lines works for every magnet. This image is here showing put many compasses around the magnet. You'll mainly map those magnetic field lines, and again they will always be from north to south. If I put a compass here, it will be away. If I put a compass there, it will be towards, and I can use that information to find north and south pole of a magnet. Just like electric field lines, we can draw magnetic field lines. When they're closer to each other, we have strong magnetic field. When they're farther away, strong B, let's say here. When they're farther away, we have a weaker B. Just like electric field. And just like electric field, at any point we can draw a tangent line to find the direction of magnetic field at that point. Here is one. I can draw another one. Let me do a better job here. Should be tangent line to my B at that point, and so on and so forth. Here are some other configurations of how north and south poles magnetic field lines looks. Same idea in different versions. We can have configurations of magnetic field. I have a north pole here, south pole. There are two different magnets. I can easily draw my magnetic field lines, and they will always be from north to south. Again, I can overall see how they form using iron fillings, and then I can draw my magnetic field lines alone, find them the direction always being from north to south. This is another example. Here we have north poles, two north poles together. They will be pushing on each other, and if we put iron fillings, we'll see that in the center here there will be a place. Not much is happening because in the middle we'll have a zero magnetic field. And here is how the magnetic field lines would look if we draw them. We'll keep drawing away from north. We can also see it here. So whenever we have a question of combination of magnets, draw the magnetic field lines always from north to south to decide what happens there. Some more configurations here for you to view. Again, we are always drawing magnetic field lines from north to south. That's the idea here. And north to south. It gives us overall how the magnetic field lines changes in a configuration. The compass is placed at black dot. We already talked about this. In which direction will the compass point? Away from north towards south, right? We have these type of magnetic field lines curving going back to south. But at this point, what I expect to see is to the right. A compass is placed up here. In which direction will the compass point? Again, the idea is the same. North to south. Away from north towards south. Here's my direction. If I keep drawing these, it will be the same, going away, farther and farther away, but in any case it will be towards left here. So that's what I expect to see there. Here's a combination question. In which direction will the compass point? North to south, right? Overall like this, passing from here I expect to see an upward direction at around this point, north to south. So this should be my answer. On the other side, how would it look? Right, north to south, it would be in downward directions over there. So my answer is D here. Right in the middle here, what would I see? Again, I would draw my magnetic field lines passing through that point. They always go from away from north towards south to the right for the one on below. I draw the other one north to south, passing from the point of interest. Overall, I can easily see away from north towards south to the left. Distances are the same, and the magnetic fields are opposite to each other. If I call this guy B1, let's say, the other guy B2, they are vectors. Magnetic field is a vector. They will add, they are opposite and equal to each other, so they will have a zero magnetic field. We will have a zero magnetic field there, so no deflection there. No magnetic field, no deflection. This part is generally talking about magnets that can be put together to strengthen and have different configurations of magnetic fields. Here we have many U magnets added together, and here's how magnetic field looks at top here. And this one tells you try in boson magnets. You can have two identical flexible refrigerated magnets for a nice demonstration of their alternating pole structure. Place the two magnets together back to back, then quickly pull them across each other, noting the alternating attraction and repulsion from the alternating poles. This will give you many magnets and how their poles are affecting each other. If you pull them quickly enough, you will hear a buzz as the magnets are rapidly pushed apart and pulled together. The pole structure can be revealed by a special film that contains fine iron fillings. We can see if we have many magnets together, like this guy here, we can see these structures using a special film, and iron fillings inside them will align along the magnetic field lines and show us that feature. Earth has its own internal magnetic field. It behaves as if we have a bar magnet in the center of the Earth. Let me do a better job here. And this bar magnet has south pole in the north geographic pole and north pole in the south geographic pole. So they are opposite to each other. And as we draw, magnetic field lines are always from north to south. We will have the Earth's magnetic field. It's a dipole field. Again, magnetic field is always dipole. There's no monopole. There's no only north or only south. And it directs from geographic south to geographic north. So it's an inverse relation. If we imaginatively follow these lines up to where we live, we will see that they are going towards Earth, tilted in this fashion as I show here, or as this figure shows, in the North Pole or close to North Pole, or north away from equator around the northern hemisphere. Here is how we will see them. And around the equator, they would be more like parallel to the surface of the Earth. They're going upright and then they will fall back down. So That's the Earth's magnetic field. There are a lot of creatures that has tiny bits of irons inside them, and those irons are affected by the Earth's magnetic field, magnetized irons, and they align along the Earth's magnetic field and help those creatures understand the direction they're going. This guy here, for example, is the magnetotactic bacteria, and it uses the alignment of the irons inside itself to understand if he's upside down or where he is in his place, and it changes its position depending on where he is. Either it goes up or down. There is an evidence that pigeons use the Earth's magnetic field to navigate by using a mechanism they have behind their head, a kind of a magnetic sensor, to understand where they are and find their way. That's it.